So I'm going to be talking about some joint work with John Cyphert, Jason Breck, and Thomas Reps on synthesizing nonlinear numerical loop invariants. And there are various applications for this kind of technology. We can use it to, say, prove time complexity bounds for loops. We can use it to analyze side channels or prove secure information flow or to prove that Fibonacci is monotone, that kind of thing. So the overall approach that we're going to take is we're going to treat a loop as if it were a system of recurrences. We're going to throw those recurrences into a computer algebra system, which will compute a system of closed forms. And then we'll take those closed forms and compute a transition formula. So this is a formula over primed and unprimed variables representing the state before and after executing the loop. So there's two reasons that this picture doesn't work out quite as nicely as it looks. The first is that our loops might not just be a system of recurrences. They might involve control flow, like branching and nested loops. They might have non-determinism. And the second bit is that the output of a recurrence solver, of one of these recurrence solvers, typically involves things like algebraic numbers, and there aren't a lot of tools in the program analysis toolbox that can reason about these things. All right, so there have been other work on using recurrence solvers to generate invariants, but I would say one of the distinctions between this work and previous is that we really focus on these interface issues. So rather than trying to compute very precise information about a particular class of loops, we're really trying to compute approximate information about arbitrary loops. All right, so for example, here's an implementation of binary search. Something I might want to prove is that it executes in logarithmic time. And the first step that I'm going to take towards doing this is to encode the body of the formula as a transition formula. The body of the loop as a transition formula. And this is really just a straightforward translation from the syntax of the programming language into logic. There's nothing fancy going on here. The trick comes in, how do we extract a system of recurrences that approximates this transition formula? Right, so this loop body does not, recurrence relations don't completely describe the dynamics of this loop. They just approximate them. I can't compute a recurrence for low or high. They behave unpredictably, but the difference is something I can predict. It always decreases by half at every loop iteration. So yeah, the trick is, how do I go from the formula to this system of recurrences? And something else that is worth noting here is that my notion of recurrence is fairly broad. I don't really mean equation. They could be inequations. They are not necessarily recurrences on variables. They could be recurrences on terms. All right, so after I've extracted these recurrences, I can throw them into a computer algebra system. It will compute this exponential closed form. I turn that into a transition relation, and voila, I have a logarithmic bound that I get by just taking the logarithm of both sides. Another example, suppose that I have this nested loop. I'm going to process this from the bottom up. So I'll start by looking at the innermost loop. I'll compute, and the innermost loop looks kind of like a system of recurrences already, right? So this is pretty easy. I just extract these recurrences, compute closed forms, and now I have a summary for the inner loop. And now I can compute a transition formula that represents one iteration of the outer loop by kind of just expanding this. Right? So I'm using the summary for the inner loop to compute a summary for the body of the outer loop. This now looks not so much like a system of recurrences. We have this existential quantifier, for example, and I can't describe the exact behavior of the j variable. All right, so a system of recurrences I might want to extract from this loop is something like this. Right, so again, I'm not describing the exact behavior, it's just some approximation. I don't know anything about J in this view. And another thing worth noting here is that these systems of recurrences can be interdependent. Right? These are not really recurrence relations, these are systems of recurrences. The recurrence for ticks depends on I. But this is something that recurrence solvers can handle. I can get this nice quadratic closed form, and I can prove that say this executes in quadratic time. All right, so the first step is I'm going to talk about how to extract recurrence relations from loop bodies. So my assumption is that I'm starting with a transition formula that represents one iteration of the loop. And so if there's any nested loops, they've already been summarized. If there's any control flow, it's encoded into the formula. And I'm going to further assume that this formula is linear. We'll get to the nonlinear case in a little bit. And our goal is to find a system of recurrences that approximates my transition formula. And by approximates, I mean that there's some linear transformation that goes from this X system into this Y system, such that every step of the transition formula is simulated by a step of this affine transformation. All right, so to put this in more concrete terms, if we remember our binary search example, this linear transformation is the thing that picks out terms that have recurrences associated with them. So it projects the system that involves ticks high and low onto the system that I actually know how to compute recurrences for, ticks and high minus low. And the process for computing this abstraction is two steps. The first step is to compute the affine hull of the formula. This is the system of all equations that are implied by the formula. All models of the formula satisfy this system of equations. And this can be done simply by querying an SMT solver for a bunch of linearly independent models. There's nothing really very complicated here. And what we end up with is a system of equations that looks kind of like this. AX equals BX plus C. Sorry, AX prime is equal to BX plus C. So now I need to go from this system of equations into a system of recurrence equations. And this is done by an iterative process of fixed point computation, where at each step of the fixed point computation, we're really just applying a linear transformation that projects out equations that can't possibly contribute to a recurrence. So we keep on projecting out equations. At each step, we reduce the dimension of the system, and so eventually we'll converge on a fixed point, and the fixed point will be a system of recurrences. And more than that, it will be the best system of recurrences in the sense that this is the maximal linear transformation, maximal linear system that simulates the dynamics of my formula. All right, so everything works out really nicely for the linear case, particularly for equalities. We can extract inequalities in basically the same way, except we have to use polyhedral operations, and we can't guarantee best abstractions, but the same intuition more or less works. So now, how do we deal with nonlinear arithmetic? All right, so suppose that I have this triply nested loop. I've already summarized the two inner loops, and what I have remaining is this formula that involves, this existential quantifier, this nonlinear term. I want to prove that this triply nested loop executes in, say, cubic time, and I want to do that by extracting a recurrence relation, this quadratic recurrence equation that's implied by this loop body formula. So how do we do this? All right, we have to throw out all of our tools that only work on linear formulas because I have a nonlinear formula. Sort of the key piece of technology that we use to extract recurrences is what we call the abstract domain of wedges. So just like you can think of a polyhedron as corresponding to the conjunctive fragment of linear arithmetic, it's just a conjunction of linear equations and inequations, a wedge is the conjunctive fragment of nonlinear arithmetic. So we can have equations and inequations that involve polynomials, exponentials, logarithms, and so on. So that's really just the syntax of wedges. We also have to reason about wedges. We have to have some way of taking a wedge and deducing consequences. And this reasoning is necessarily incomplete because this is an undecidable theory. So we just want to do as best a job we can and not worry if this is not a decision procedure because it won't be. All right, so the reasoning on on wedges is really based on these two different views of a wedge. The first view is as a polyhedron. So we can think of a wedge as a polyhedron by just treating each nonlinear term that appears in an equation or an equation as an independent dimension. So if we have an n squared, we'll just forget about the fact that that's actually a representation of n squared and just treat it like any other variable. The other view is to view the wedge as an algebraic variety, a system of polynomial equations. And we obtain this view by just forgetting about all the inequations and treating each non-polynomial term as an independent dimension. And algebraic varieties are something we can reason about using, say, Grosvenor basis techniques. And we can communicate between these two different views with the common language of linear equations. So if we derive linear equations, we pass them back and forth. And on top of all of this, we add some inference rules for inferring linear inequations, or sorry, not linear inequations, but inequations, and some congruence closure techniques to reason about these functions, such as exponentiation. All right. The key operation that's supported by the wedge domain is symbolic abstraction. Symbolic abstraction is the operation that takes a formula and computes a wedge that approximates it. Or you might think of this as trying to find all of the equations and inequations that are consequences of this formula. Right? It's not going to be all of them, but we'll try to get as many equations and inequations as possible. So the way we would handle our loop body that we saw before is by first taking this existential quantifier and skolomizing it and moving this disjunction out so that we're really just looking at the disjunction of two wedges. Right? These are just conjunctions of equations. We have two wedges on one side. All right. Then we apply our inference rules to find equations and inequations that are implied. And we use some Grosvenor basis techniques to project out these Skolem constants. Now we take the polyhedral view and just compute the join. And voila, we have this recurrence inequation that we wanted before. All right, so the high-level process is that we start out with some nonlinear formula, we compute a wedge that over-approximates it, and then we extract recurrences from the wedge. And the process for extracting recurrences from a wedge is similar to the one I already described for the linear case based on this fixed point iteration. The mathematics gets hairier, but the intuition stays the same. And the class of all recurrences that I can extract using this technique correspond to systems of equations in which we have this additive term that involves polynomials and exponentials. So now the question is, how do we solve these systems of recurrences? And the technique we're going to use to solve this is operational calculus. So operational calculus is an algebra of infinite sequences in which the idea is that we can translate recurrences into an equation in operational calculus, just as a standard equation, not a recurrence equation. We can solve for x in this equation, and then we can translate the solution back into the language of classical algebra. So we do this transformation, solve, transform back. To give you some background on operational calculus, the field of operators is a field. An operator is a sequence which has infinitely many positive positions and finitely many negative positions. So for example, this A sequence has two negative positions, A minus 2 and A minus 1. This B sequence has no negative positions. We can add two sequences by adding them up pointwise. We can multiply them by taking this convolution difference. You don't need to understand the convolution difference. The thing you need to understand is that there is a left shift operator. So this element Q, which consists of a 1 in the negative 1 condition and then position and then 1s forever on, has the effect that if we multiply a sequence by Q on the left or right, what we end up with is the same sequence shifted one position to the left. All right, so the way that we translate recurrences into equations in operational calculus is by thinking of this variable x for which there's a recurrence as defining an infinite sequence. So it's just some variable in operational calculus. And then we use the left shift operator q to rewrite this recurrence equation as an equation. So we want to, so this x to the power k plus 1, which represents exactly this sort of shifted operation. So if we multiply q by x, we shift left, then we need to knock out this x0, so we have to subtract this q minus 1 times x0. But the result is we have the exact same sequence, just shifted to the left, and now we equate that with the unshifted sequence plus some additive term. And the additive term is translated using this t sub k function into the operational calculus. All right. And any expression that follows this grammar can be translated into the operational calculus just by some simple pattern matching rules. I'm not going to show you all of them. The point is this language of additive terms that we have for recurrences can all be translated into operational calculus. All right. So we're in the land of operational calculus. It forms a field, so we can apply all of the usual algebraic tricks to get a solution for the x variable, and then we want to translate back. And to translate back from operational calculus into classical algebra, we're really just applying the inverse of the transformation we applied to get into operational calculus. Right, so we're really just pattern matching on these operational calculus terms and translating them to their equivalents. The problem with this is that the pattern matching is incomplete. There are operational calculus terms that don't have any corresponding classical algebra interpretation. And the reason for this is exactly because our version of classical algebra doesn't admit algebraic numbers. So we fail to find an operational calculus translation exactly in the situation that a classical recurrence solver would return a closed form solution that involves an algebraic number. So what do we do with these terms that are untranslatable? Well, the way that we communicate this back to logic is by just introducing a function symbol. So we associate this a new function symbol with the term t that we couldn't translate, and now we can use formulas that involve this uninterpreted function symbol. All right, and the wedge domain has no trouble reasoning about uninterpreted functions. We can use our SMT solvers. Everything's fine. But this isn't quite the same as using an uninterpreted function. This isn't uninterpreted, it's implicitly interpreted. There is an interpretation of this function, it just lies in the operational calculus world rather than the algebra world. And the practical effect of that is that we can extract recurrences that involve these operational calculus function terms, and we can translate those back into operational calculus just by remembering where that function symbol came from and translating back to the operational calculus. Okay, so I've described how to extract recurrences and how to solve them, and here's how it works in practice. So the tool that I'm talking about is ICArray. It was built on top of Z3. It uses Apron for polyhedral manipulations. It analyzes recursive procedure using a technique that we presented at PLDI last year. And we ran it on a set of benchmarks. OLA is the Dilligs et al. It's a set of linear benchmarks, but we wanted to compare against these software model checkers. This is Ultimate Automizer, CPA Checker, and Seahorn, which do better on linear examples than nonlinear examples. The functional and relational categories are a mix of linear and nonlinear properties. The functional correctness, the functional category is functional correctness benchmarks like proving that multiplication does what it's supposed to. The relational category consists of things like secure information flow properties. And we can see that ICRA performs admirably well. It's quite a bit faster than the other tools. It can prove more assertions, except in the linear category, but it's still very competitive in the linear category. And that's pretty impressive considering that ICRA is sort of just an invariant generator. It does not perform any abstraction refinement, which is kind of the backbone for these other software model checking tools. All right, so summing up, the contributions of the paper are the wedge abstract domain for reasoning about nonlinear arithmetic, this algorithm for extracting recurrences from wedges, and this operational calculus-based recurrence solver that avoids algebraic numbers in their closed-form solutions. All right, and that's it. Thanks.
So I see in the 70s it was very popular, the difference equation, and you made a lot of progress. But I have not understood how you handle conditional, which was the mess. For example, if you say tick is, if it's even, I divide by 2, else I add +1. Can you handle this?
So you have a conditional where on one branch you multiply tick by 2 on the other end?
No, anything. That is, you have conditional in the equations.
No, so we don't allow conditionals in the equation. So the way that we deal with conditionals is that...
Outside, yes, outside.
Outside?
So that you can make a case analysis, more or less, no?
No. So we don't do the thing where we blow up the set of paths and compute a different summary for every loop path. We won't move the conditional outside the loop. What we'll do is try to find all equations that are implied by the loop, which convexifies it. Right? It's like taking a join operator.
But in the matrix formulation, you have no conditional inside the...
Right, yes, yeah.
So, still more work to do.
So do you want to?
So we have some questions from Slido. So the first question is, does your fixed point computation terminate in the linear case, or does it need a widening operator?
So for the case of linear equations, there's no need for a widening operator because each step of the fixed point iteration decreases the dimension of the matrix that you're working with, and it's a finite dimensional matrix, so eventually it'll terminate. For the case of linear inequations, we're dealing with the domain of polyhedra, and indeed we use a widening operator to ensure termination of this process.
So we have quite a few Slido questions. The second question is, do you need to provide any templates for the classical algebra function in the step that translates from the operational calculus into classical algebra?
No. No, there's no sort of smart synthesis going on that translates from operational calculus into classical algebra. It's really just pattern matching. Yeah, it's.
If there are no questions in the audience, I have one other question from Slido. So the question is, if your approach solves the Fibonacci recurrence equation, how can you determine the necessary nonlinear terms?
Yes, it will solve the Fibonacci equation, but so here's what happens. You end up with these. You solve it in the sense that you will find one of these operational calculus terms that corresponds to a solution, but you will not be able to translate it into standard algebra. So this is something that you could do if you wanted to factor the polynomial over the reals, but it's not something that is currently done.